The next type of power that we're going to study is wind power. So the interesting thing with wind and solar and hydro as well, which we're going to study in a little bit, is that they all come from the sun. The way that this happens is that you have your solar energy coming in, the radiant energy. It heats the air. This drives convection currents, these convection currents themselves are wind. Okay, so we take the kinetic energy from the wind, turn it into rotation of the turbine, and that then is transformed into electrical energy, as we always have happen with that rotational energy of a set of magnets in a coil. Okay, so we actually have the derivation here to consider. All right, the power that's going to be delivered by a wind generator. So as I often have done in my career, we consider a column or a tube of air. Okay, typical engineer derivation here. This is sloppy, just an approximation, as many of these engineering derivations are, but they work. So what I'm going to use here is the Greek letter rho to be density. I'm sick of high schools using d. You are going to use grown-up variables now. Use rho for density. Okay. So the mass is going to be equal to rho times the volume, density times the volume. Okay. The speed with which the wind moves here, okay, it's going to move the distance d, given right here, based on our kinematics. So d is just going to be equal to the speed times the amount of time it's flying for. All right. And so the volume that we have of air here, by the way, we have some radius r. All right. So what we can find is the area, multiply it by the height. It's a column or a tube, right? A cylinder volume. So we see that the volume is going to be equal to pi r squared times d, okay? And what we can actually end up doing here is do a little substitution for this. So we get pi r squared, right, times v times t, okay? Substituting in our definition of d, all right? So now we have this for the volume. So if we plug this into m, all right, remember m is just going to be equal to rho times v. What we end up with here is rho times pi times r squared times v times t. Okay, so that gives us what our mass is, okay, of air going into this wind turbine. From there, all right, we can actually calculate the kinetic energy of that air. It's just 1/2 mv squared. If we take our new definition of m and substitute that into this equation right here, we're going to have one long little equation here, and I'm going to not combine these v terms yet, okay, and once we do combine them, we have something a little bit easier to deal with. Alright, there we go. And so that tells us how much energy is being delivered by the wind, okay, in this tube of air. And if we want to know, all right, the rate at which it's being delivered, all right, remember it's just the change of energy, all right, per time, or transfer of energy per time, okay? So what I'm going to do is I'm just going to take this whole thing right here, our 1/2 rho pi r squared times v cubed times t divided by t. What we see is that our t terms drop out, and we're left with 1/2, all right, rho times the air. I'm actually going to change that back, times v cubed as the power delivered by our wind turbine. Okay, so we see that the power, all right, delivered by wind depends on the velocity of the wind to the third power. That's pretty interesting there. Okay. So again, this equation is just an estimate because not all of the kinetic energy from the wind is delivered to the turbine. Okay. And density is going to vary, right? It is not a constant. And so yeah, that's the main thing. So it's impossible to extract all this energy out because you can't just stop the wind. You need some of the wind to flow through, all right? Some of that air to flow through in order to continue to have power being delivered to the turbine. So that's why it's impossible to extract all that power from the air. So this gives us just maximum power possibly delivered by the wind, really, is all it's going to tell us, all right? And you also have friction, you know, to consider typical efficiency measures. So yeah, and then, you know, these turbines, what we do is that we place them separate from each other, okay, so that we don't have turbulence issues in it, so that, you know, the kinetic energy can be captured as much as possible by each turbine. Kind of an optimization thing there, all right? So we have a couple of problems here, typical types of problems that you might have to solve. The first one is that we have a wind turbine that has a rotor diameter of 20 meters. It has a wind speed of 25 meters a second on some day, all right, when the air density is 1.3 kilograms per meter cubed. So we want to know what is the power that can be produced if the turbine itself is 30% efficient. All right, so given that the radius here of these rotors is going to be 10 meters, with the diameter being 20, wind speed 25 meters per second, with the air density here, all right, 1.3 kilograms per meter cubed. And so we can figure out the area pretty easily, all right, pi r squared, all right. And so the power input from the wind is just going to be that 1/2 rho times the area times the wind speed cubed. When we put all of this in, we get 3.19 megawatts, all right? And given that the efficiency is only 30%, the actual power output here is just going to be that efficiency times Pn, and when we plug that in, we get 957 kilowatts, which is a very, very large wind turbine there, okay? All right. And that's a very, very high wind speed to be calculating this for. That's like 50 miles an hour. So that's pretty unrealistic, but hey, it's practice. Okay. Number 2, we have a wind generator. It's being used to power a solar heater pump. Okay. So this is more of a local scale, right? So if the power of the solar heater pump is 1/2 kilowatt and the average local wind speed is 8 meters a second, and we have the air density there, we want to deduce whether or not it's going to be possible to power the pump using the wind generator. So if we look at the equation here that we use to figure out the power equals 1/2 rho times the area times v cubed. Okay, so we have the power that we need, we have the wind speed, we have the air density. So the only thing we're left here is the area. So what this tells us, okay, is that we're probably going to end up solving for r, and they're asking would it be possible, okay, is r a size that is reasonable for an operation on this scale. Okay, that's what the question is. So, in a residential situation, you're going to have a small turbine, right? And the turbine size could be, and you have a radius anywhere from 1/2 meter to a couple meters, all right? So when we solve for the size of this thing, okay, after a little bit of algebra, the area that the blades sweep out is going to be this, okay? So it's 1.8 meters squared, and once you solve for r is equal to 0.76 meters, and this is absolutely feasible, okay? So yes, possible. All right, so there are some advantages and disadvantages to wind power. When you come to the next class, we'll talk more about this type of power.